real-world robot planning faces a fundamental conflict. PDDL provides structured, interpretable reasoning and is highly friendly to large language models, but it assumes the environment is fully observable and deterministic. On the other hand, partially observable Markov decision processes, or POMDPs, offer rigorous modeling of uncertainty. Yet constructing and learning POMDP models for real robotics domains remains labor-intensive and difficult to scale, especially with visual inputs. Researchers from Shanghai Jiaotong University propose PO-PDDL to solve this. PO-PDDL is a symbolic formulation that unifies the relational syntax of PDDL with the uncertainty modeling of POMDPs. It introduces observable schemas, stochastic operator effects, and symbolic observation rules, allowing LLMs to generate robust planning domains that handle partial observability and stochastic transitions. The method learns these domains directly from visual demonstrations of robot policy executions. The pipeline operates in two distinct stages to ensure model quality. First, it learns a fully observable symbolic model by reconstructing latent state trajectories. Using forward-backward inference, an LLM analyzes video frames to infer hidden state changes and stochastic operator effects. This step builds a transition model that captures execution uncertainty, clustering observed state changes into probabilistic effect modes that account for manipulation failures. Second, the system identifies partial observability by detecting contradictions between the reconstructed symbolic states and the visual observations parsed from the video. Where mismatches occur, the pipeline defines observable schemas and learns symbolic observation models. Crucially, it distinguishes between passive observations, which rely on standard visual grounding, and active perception actions, which are explicitly modeled to gather information about hidden predicates. This mismatch-based mechanism ensures the observation model only captures genuinely uncertain aspects of the state. With the PO-PDDL domain learned, the robot performs online belief space planning. It maintains a belief distribution over symbolic states and updates this belief via Bayesian filtering using the learned transition and observation functions. The planning problem is solved online using the DESPOT solver, which samples state hypotheses and searches a sparse belief tree to maximize expected cumulative reward, all while respecting interaction constraints. Experiments on real-world long-horizon manipulation tasks demonstrate the power of this approach. PO-PDDL achieves a 100% success rate across all evaluated tasks, consistently outperforming baselines like Uni-Domain and POMDP, as well as direct VLM-based planners. It successfully handles complex constraints, occlusions, and stochastic skill execution, achieving robust task planning with significantly lower planning costs. PO-PDDL represents a major step towards scalable, data-driven robot planning that can reason effectively under the uncertainty of the real world, making reusable POMDP models accessible through visual learning.